Hi. I'm just typing in. I got 3 people, 2 likes already. That's amazing. Thanks to the people who checked in. We'll wait just a few more minutes and then we'll get going. The sheet is called Measuring Forces, so make sure you have that open. I gotta move this. Over here. See if you can see the table. Fantastic. All right. This may or may not work from this distance. We'll see. Jacob, Ava, Connor. Hopefully some others will show up. It'll be easy to do if you're here. That's fantastic. Thank you. I'll start in about 40 seconds. You can see all the things that I have here in front of me will all be used for measuring forces. I'll see those in a minute. Hi, Cadence. What you can think about is, what force would you like me to measure first? What force would you like me to measure first? You learned about the 9 different forces and where you see them. Okay. And you probably looked at the assignment. That's going to be a slideshow of the forces in your house. We talked about that right at the beginning of this term, how one of the reasons why I love teaching science is for us to be able to see science all around us. Hi, Hannah. So I hope that you'll be able to see all these forces around you. And I mean, I could do this all day, right? There's all sorts of forces around us. So, someone pick a force. Write down a force. Write down a force that you would like me to see me measure. Hi, Riley. That you would like to see me measure first. Oh, I'm going to get something from upstairs. Hold on. All right, what force have we got? Gravity. All right, fantastic. Thanks, Manita. So we're going to measure gravity force first. Now, gravity, there's a whole lesson that we're skipping. There's a difference between mass and gravity. Gravity, this is 500 grams. That means there's 500 grams of stuff in here. Okay. Gravity is the pull of the Earth on this object. So if I go to the moon, the gravity is different. It's 1/6 of what I have here on Earth. So gravity, okay, is the pull of something towards the center of the Earth. All right. Now, these things, I've got 4 choices here. They're kind of broken because of an experiment that we're going to be doing later on. But they still work. These are called, well, I'm going to call them newtometers. Okay, they measure newtons. Forces are measured in newtons. And that's going to get important next week when you learn about work. So this 500 gram weight, I better do a different one. This 500 gram weight is pulled down to the center of the Earth with 5 newtons. There's a mathematical connection there. Again, it's in the lesson that we're skipping. Okay, but 500 grams, 5 newtons. There's a connection there, right? Divide the grams by 100, and you get the number of newtons. Okay, so this is how many. Okay, so this is being pulled down by 5 newtons to the center of the Earth. This is 1,000 grams. Any guesses? Any guesses? Oh no, this is a 500 again. Where's my 1,000? There it is. This is my 1,000. Okay, so it's going to be pulled down the center of the Earth by, if 500 was 5, 1,000 grams is going to be 10 newtons. Okay, now you may think, oh, it's just weights, but anything is pulled down to the Earth. So this is being pulled down to the Earth by, ooh, that's over what I can measure on this one. They all have different measuring capacities. This one's being pulled down to the Earth by about 17 newtons. Okay, I'm what am I? I'm 80 kilograms. Okay, so I'm being pulled down to the center of the Earth by 800 newtons. Okay, so you add a 0 to the grams, to the kilograms. Okay, so everything is being pulled down to the center of the Earth by the force of gravity. This is being pulled down by 0.5 newtons, actually 0.4 newtons. Okay, this is being pulled down. I don't have anything else here. This is being pulled down to the center of the Earth by, it's not even measurable on that one, by one Newton. Okay, so that's the force of gravity. Everything's being pulled down to the center of the Earth. Okay, so you can pick any one on the measurement sheet. Just pick any one of those things and write down any measurement that we just measured. Okay, you don't even have to identify what it is. All I want to look for is that you understand that it's measured by Newton. So beside each of the numbers you put down, just put down newtons. So we have 10 newtons, 5 newtons, 17 newtons. Okay, all those things are being pushed down by something, some force. Okay, gravity by newtons. Okay. Next one, electrical. Riley, I cannot figure out how to measure electrical. I looked into it. There's a really neat experiment, like the really simple one, okay, is if I take a piece of paper, okay, rip it up into smaller pieces, okay, grab my balloon, one of them at least, rub it on my head, okay, and put it down, okay, actually it's not working. The humidity is really high down here. Try again. It's not working. Normally when we do this, these pieces of paper jump up, okay? Jump up to the balloon. Oh, it's not working. But I cannot figure out. Oh, can you guys hear me? Just let me check. You guys hear me? It looks like it. Okay, thanks Connor for the 10. You're absolutely right. Okay. Yeah, it's not picking it up. Okay, but normally, and you can picture this too, right? Maybe you can measure the amount of static electricity in my hair, how much force of static is being pulled. But I can't hook up one of these to my hair or to one of these pieces of paper to see how much force is being being used by electrical force, static electrical force, okay, in order to pick it up. So I love the suggestion, and you just need to know that that's only static electricity, not the electrical. I mean, I could stick this in an electrical socket and see how much force hits me, but that's not the way it works. That kind of force is different. So this force is only referring to static electricity. And it gets important when you deal with chemistry, okay, that there's bonds that form because of indirect ions, okay? So lightning is an example of static electricity. It has a huge amount of force that can blow apart a tree, right? So you can picture the force, but I can't figure out a way to measure it, okay? Love the suggestion. Other force that I can measure. Jacob says shearing force. Shearing force. Now, shearing is the force of cutting. Okay. So how much force do you need to cut something? All right. Now, I tried this earlier. It's a little difficult. Okay. But if I can hook my Newton meter, okay, up to this pair of scissors and see how much force is needed to pull down and cut. Okay. And it's measuring probably about 4 newtons. So it takes about 4 newtons of force to cut this piece of paper. Now, that's just a regular 8.5 by 11. This is sandpaper. Okay, rough sandpaper. Is it going to take more or less force? More or less force? More. Well, let's check. Okay, so I'm going to put my scissors here again. Okay, I got to get it started. Okay, balance it. And it is up to about 16 units of force. Okay, 16 newtons is needed to cut this. So we experience every day, right? You know that some things are harder to cut than others. If your scissors are dull, you need more force because the shearing force of those scissors is less. It depends on what you're cutting, right? If I cut regular paper or cardstock, if I use tin snips to cut aluminum, those all require different amounts of forces. So you can feel it in your hands, right? If you cut something for a while, especially aluminum, the siding, which I've done before, it takes a lot of force and it breaks down your hands. So that is, actually, that's an interesting one. Grip force would be one. I'm not sure what force it would be, but you see that you hear that phrase a lot, grip force, in, I can't think of the show, that Ultimate Warrior, I think, okay, where they have to do these obstacles, and the grip force is really important, okay? But the force, shearing force, is the force needed to use scissors or an axe, right? If you're cutting wood, okay, same thing. You need a huge amount of force to cut that wood, so that's your shearing force, all right? So we've done gravity, we've done shearing, tried to do electrical, I explained it a bit, but that's all I can do. Ultimate Beastmaster. Thank you, Jacob. I knew I couldn't think of it for the life of me. Ultimate Beastmaster. Okay, they talk about grip force a lot. Magnetic force. So I've got a couple different magnets here. Okay, and we're gonna see how much force is needed to pull it off of this metal stand. Okay. So this is a fairly weak magnet. Okay, so it's actually a better way to do this is to put it on here. Okay, so I have a magnet acting on a magnet. So how much force is needed to pull this magnet off? Okay, so this is, like I said, it's a really weak magnet. So this is not a good choice of a one. Okay, and again, just because of where we are and what we're doing, these are all experiments that you would be doing. All right, and one of the first labs for this one. So magnetic force, this one, oh gosh, it's like 0.1. 0.1. So very little magnetic force in this. So when we refer to a magnet as weak, right, when things start falling off your fridge because the magnets become weak, okay, that's what we're referring to, the magnet force. Magnetic force. So this is like 0.1. Let's do 0.2. 0.2 newtons is how much force is needed to pull this magnet from this magnet. Now, I have different magnets here. So if I wanted to pull, there, that's a stronger magnet. So if I want to pull this magnet from this one, sorry, I got stuck in the metal stand. If I wanted to pull this magnet from this one, okay, so I hold this one, try to pull it off. Okay, this one has a magnetic force of 6. Okay, so it took 6 newtons of force to pull this magnet off of here. All right, so that's magnetic force. Now in here are some really phenomenal magnets. These ones that are just about impossible to get off of anything. There we go. So this one, okay, you can, right? It sticks pretty hard. I have to slide it off. And you've probably experienced those kinds of magnets. That's a very, very strong magnetic force. So if I do the same thing, I put it here, all right, and then try to pull it off. So I hold this, try to pull it off. Let's see if I'll do a count. 10, 15, about 12 newtons of force. Okay. Now that's partly because of the size, but okay, you get the idea that this is a very, very strong magnet. About 15, between 12 and 15 newtons of force. So different magnets have different. This is a fridge magnet. Different magnets have different newtons of force. You probably have played with some really, really strong magnets at some point. So that's magnetic force. And again, you can choose any one of those numbers. It doesn't really matter. All I'm looking for is a number and the word newtons behind it, just so it reinforces in your brain that force is measured in newtons. All right, what else have we got? Whose birthday? Great question, Kaylee. I actually had to go to this. Oh, well, why don't you tell me what force is acting on this balloon? I had to go to Buck or two this morning to pick up these because there's a particular force that this shows really, really well. Okay, so we'll get to that if someone mentions it. If not, I'll just mention it. Let's see. Tensile force. Thank you, Riley. Tensile force. Now this is the reason why these things are broken. Okay. Tensile force, is the force of, write it in there. Tensile force is the force of, write it in there. No, you don't have to write what it was, Cadence. That's not important. Okay, I'm just looking for a number and the word newtons behind it to show that you were listening and to just reinforce the idea, because that's going to get important next week. Riley, tensile force is the force of what? Pulling. Thank you, Jacob. Okay, it's the force of pulling. So I've got string here, yarn. Okay, so I'm going to see how much tensile force I have to put on it before it breaks. All right, so this is yarn, and as you're thinking about this, you're thinking about your slideshow at the that you have to produce by next week, Wednesday. So where do you see tensile force? Where do you see pulling? Okay, and it can be, you don't need a measurement. You just need to show me that it's pulling. So even simple things, like I see over here, we have a light hanging from the roof. Well, the light, okay, that's hanging on the electrical wire is using tensile force, or shows tensile force. Okay, so this is yarn. And I'm going to see how much tensile force I have to pull on, I have to use in order to break the string. Okay, so you got to turn it this way. So I'm up to 10, 20, 30, 40, 50, still not broken. So that's about, there you go. Okay, so that was about 55 newtons of force was needed to break that string. So that's a good example of tensile force. Okay, now a lot of these forces are all in combination. Remind me to talk about something later on. It's normally a quiz, but maybe I'll give that as an option for next week. Actually, that might work really well. Let me think about that one. Okay, so here's another string. Okay. All right, it's this stuff right here. Okay, so is it going to be more or less? So this is what I just used, and it broke at the tensile force of 55. Okay, 55, 60. Okay, this is a much lighter string, so it should be less or more. Hi, Emma. It should be less. Okay, good. So let's take a look. Okay, so I'm using newtons. 2, 4, 6. Okay, so that's only 6. That's like a tenth of that. Okay, so that's tensile force, and you measure pulling. Okay, so picture things that are pulling. One of the exercises that I think I'm going to throw in for next week, maybe it's a different one for the slideshow. Let me think about that one. Because what's neat is that these forces, like I say, right, I wanted you to see them everywhere. I know that my class is seeing it next week, but you have already seen it. You know that Canada's Canada's Wonderland virtual tour? Okay. Well, think about all the forces you see in there. Okay. I clicked on one link yesterday with my class, and it was the swings, right? The swings hang down and they go around. Well, there's tensile force on those swings. Okay. Gravity's acting on you. Gravity's acting on you bigger because you're swinging around. But there's tensile force on those chains. All Canada's Wonderland, all of those parks base their existence on the idea of forces. In fact, Canada's Wonderland actually offers a place where you can go, and they offer a course where you go to Canada's Wonderland for the day and study physics, which would be kind of fun. But maybe that's an exercise you can do. Okay. I might throw that as an option next week, right? If you don't want to do the slideshow, okay, go through that and just see if you can find different forces. Buoyancy would be pretty hard, I think, unless you can get on the water slide, because water slide works by buoyancy force. Okay, but these forces are everywhere, right? Magnets are going to be in your roller coasters. Okay, that's what helps keep it on the track. Tensile force, I've already talked about. Gravity is everywhere, right? It goes up, 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 up. And the reason why you go down is because there's a gravity force. There's a force of gravity acting on it. Shearing. If there's a bow and arrow game, okay, so you pull the bow and the arrow goes in, and the reason why the arrow goes in is because it has shearing force. Okay. What other force? Pulling buoyant force. Okay, so looks like we got tensile. Looks like we're doing buoyant force. Okay, so I've got two things to measure buoyant force. One is this. Okay, so buoyant force is the force acting on something, pushing it up. Okay, we talked earlier about density. It has everything to do with density, but we're just worried about the force right now. Okay, so how much force is acting on this in order to push it up? So if I use this one, these new ones that I got that broke, have this other device on it that I can push down on. Okay, so let me just see what I can do here. Okay, that's not even going to measure anything. Okay, so let's do. It has hardly any force on this one. Let's see here. No, it got like 0.1. Okay, now ideally I would find something bigger, but I didn't. I'm not going to find anything like this. Okay, so 0.1. There's a 0.1 buoyancy force acting on this. What I like about this is it gives us a chance to talk about when forces are unequal, okay, because the force of gravity is pulling this thing down, but the force of buoyancy is greater, so it's pushing it up. Anytime that happens, and the force going one direction is greater than the force going another, and there's a great Veristadium video showing this, then you have movement. So if this is moving up, is going up, because the force of buoyancy is greater than the force of gravity pulling it down. Okay, and it's like 0.1. Okay, now Kaylee, this is the reason why I got these balloons. I don't know. They're pretty, I don't know if I'll be able to measure anything on it. They're pretty light balloons, obviously. Okay, so just put a knot in here. And I'm going to grab my lightest one. It's 22.5. Okay, let's see here. So this is buoyancy force. So how much buoyancy does this balloon have? Okay, so this balloon, it's not even measuring. Maybe I need to use 2. Yeah, the force of gravity actually acting on this is greater than the force of buoyancy. So let me just adjust it. I don't think it's going to measure anything. I'm going to try 2 balloons and see if that helps. That's why I got 2. And also just in case one broke. So the force of buoyancy, again, like 0.1. Okay. Let's see. No, not even 0.1. Like, yeah, 0.1. 0.1 newtons of force is pulling this thing up. Now, if I put 2 on here, maybe I'll get something a little greater. So again, okay, force of buoyancy is pulling it up. The gravity is pulling it down, but the force of buoyancy is greater, which is why things float. Let's see if I can just tie this in a knot. So I put this one on. And now I've got hardly anything. And this balloon is actually under that one, like 0.2. Okay. Hardly any buoyancy force on these. Okay. But it's enough to overcome the gravity pulling on them, which is kind of cool. So if you picture the movie Up, right, all those balloons, okay, have a buoyancy force that pulls it up. And if that house, whatever that house weighs, it has to overcome that weight of the house. So that's how much buoyancy force it had. Okay, so very, very little. So that was $4.50 worth of an experiment that I bought this morning. All right, so that's buoyancy force. Okay, a little bit here, right? Boats. Okay, so this is one example of buoyancy force. That's another example of buoyancy force. So it's a force that pulls up. All right, very little. I mean, on a boat, it would be a whole lot. On up, it would be a whole lot, but maybe on other ones, maybe not. Oh, Emma, I tried to do electrical force, and we had the conversation how difficult it is to measure. I rode the balloon in my head, and you saw my hair stick up. So there's a force there, but I can't tie one of these to my hair to see how much force is on. Another force. I got to scroll up. We got tensile. We got buoyancy. Have any ones? Gravity. We did. Shearing. We did. Okay, shearing with scissors, magnetic we did. What other force? Friction. Okay, so let's do friction first. Okay, friction is really easy. It's acting on everything. Okay, if there was no friction, there's a great weird connection, great magic school bus where they get rid of friction. And you see these people sliding all over the place. So friction is really good and what allows us to walk. All right, but it's really, and it allows the tires of the car to go. Right? When it frictions against the ground, right, it pushes it forward. Friction is also really bad. I tell the story about how when I was going down, when I was living in Indonesia, we went down a mountain. You can picture this, right? Try biking down Victoria without using your brakes. Victoria Street in Beansville, all right? Or any one of the escarpment roads, right? You're going to go flying down on the bike. So you use your brakes, right? And as you use your brakes, okay, it becomes hot. The rubber friction against if you have that kind of brake, friction against the tire, right, causes heat. So friction causes heat, which we already knew from our heat unit. So friction is just pulling things. And this gets important when we talk about civil machines. So how much friction is acting on this thing? Okay, so I grab it. Okay, and there are 11 newtons of force, 11 newtons of friction force acting on this, pulling against the table. So I have to overcome 11 newtons of force in order to get it to go. How do we reduce friction? What can I do to this to reduce friction? Right? Or to this, actually. What can I do to reduce friction? And that's one of our goals, right? Oftentimes, one of our goals is to reduce friction so it doesn't produce heat, okay, especially in an engine. So what are some things I can do to reduce friction? I can't guarantee I'll try all of them, but what's something I can do to reduce friction? Besides reducing the weight, okay? Reducing the weight will reduce the friction, okay? But what can I do to reduce the friction on this? Or increase the friction? Let me talk about that first. Okay, since nobody's writing an answer. As I'm doing this, think about it. Okay, so now I'm going to use my sandpaper again. I'm going to put the sandpaper here. Okay, This is going to get tricky. But the sandpaper should increase the force. Okay, good. I'll see if I can get some. Okay. Sandpaper should increase the friction because this is all here. Okay. So it was, I don't remember what it was. Okay. I think it was 12. Okay. As I pull it, okay, now it's up to about 22. Okay. 22 newtons of friction acting on it. Now, Jacob said oil or Vaseline, okay, 11, okay. What other, so let me try oil. Try my WD-40. Okay, so here's some WD-40, okay. Again, one of the advantages of teaching at home. WD-40, okay, that should decrease the friction. Okay, let's see if that works. So we worry actually as humans about friction a lot. Okay, now it's about 10. Okay, so we reduced it a little bit, but not a whole lot. Okay, so oil, we use oil to reduce friction. One of the things you may have seen, okay, if I put a bunch of straws down and put them on the straws, that should reduce the friction as well because they're going to roll in the straws. Okay, so now the friction is 5. Okay, but actually it's pulling it along. Okay, so friction is a force that we end up worrying about a lot, but it is a force. All right, you're going to learn about simple machines and how it affects simple machines next week. Thanks. All right, so friction. All right, so friction acts on everything. Let's see, what else have we got? Oh, was it 11 originally? Oh, it should have worked. All right, let's see, compression. All right, so I have one thing for compression. Okay, so this is a syringe. Okay, and it's got plasticine stuck in the bottom. All right, now the plasticine is there to stop it from pushing around. Okay, so what I can do is I can go like this. Okay, and I've got to use compression. Okay, because I'm compressing the air in here. We learned about compression air and heat unit. Okay, to get it to move. So how much compression force can I put on here? Okay, it's moving down. It's all the way up to 50 already. Okay, in order to get it moved down, it's actually about 60. Okay, so that's about 60 newtons of force is needed to compress this syringe. Now, if I use this one, okay, I can also compress my balloon. Hey, these balloons are really coming in handy. Okay, I can also compress this balloon. So how much force is needed to press the air in this balloon? Okay, so I'm pushing it in, and I can use more or less. Okay, but I can do it all the way up to 10. Okay, now what's kind of cool about that, and we talked about this, right? If forces equalize, okay, and if one force is greater. So if I keep compressing, if I use this one to compress this balloon, eventually the compression that I put on here will overcome the elastic force, which we haven't talked about yet, the elastic force in this balloon. Okay, and that's what makes it pop, because the compression force, or the shearing force that I use to poke this balloon is going to overcome the elastic force, and it's going to pop it. So again, when one force overcomes another force or is stronger than another force, you're going to get a change of some kind, whether it's a change in direction or a change in properties. All right. So compression force is the force of pressing. Okay, so we use the syringe to press. Okay, how much force is needed? Okay, you compress a balloon. You can compress all kinds of things. Okay, so I'm thinking about where you see compression in your own homes, or at a roller coaster, or as Canada's Wonderland. Sometimes you get those things that you use a hammer for and weighing it. Okay, and then it goes up. Okay, sometimes that works by compression force in your home. A turkey baster. Okay, if you don't know what that is, ask your parents. So turkey basters works by compression force. Anything you squeeze, okay, works by compression force. Okay, usually has to overcome actually elastic force, except in this case. Okay, that is just overcoming the pressure of the air pushing up. All right, compression force. Nope, we haven't done elastic yet. Awesome. Okay, bicycle pump. Awesome example, Hannah. Okay, that's a really good example of a compression force, right? How much force do you need to push down on your bicycle pump? Okay, I don't have one here. Otherwise, that'd be a great idea, Hannah. Let's see. Elastic force. Elastic force is a good one. Okay, so I've got two elastics right here and here. This elastic force, it looks the same as tensile force, but it's different. Okay, it looks the same as tensile force because I'm pulling it, but what we can actually measure on an elastic, okay, is the amount of pull the elastic wants to do in order to get back to its original shape. That's what elastic force is. It's not the amount of pulling, it's the amount of force that wants to come back. Okay. We didn't have a newtons for electrical. I think I even wrote in there. I don't know how I'm going to measure that. So you can just skip that electrical. Okay. So elastic force. So I have a couple of examples and a couple of different ones that you may not think about when you think about elastic force. Okay. So this one is a fairly weak elastic. Okay. So if I put that on here, okay, it has an elastic force of about 4 newtons. All right, so it's pulling back, trying to get back to its original shape with a force of about 4 newtons. Okay, but you can see where it looks like tensile force, but it's actually measuring the force back. Now, this is a much stronger elastic. And this one measures at about 9 newtons. Okay, so it's pulling back with 9 newtons. Now, what people don't often think about with elastic force, because on the slideshow you'll notice, and in fact almost everyone did, is they use elastics to show elastic force, right? They went like this. Hey, look, elastic force. Okay. Now they used hair bands because that's where you see electrical force, elastic force. Okay. But here's another really good example of elastic force. Okay. In here, there's a spring. Okay. That spring is actually elastic force. So anything with a spring is also elastic force, but it's the opposite. Okay. This one wants to get back together by pulling. These ones want to get back together. Springs want to get back together, back to its original form by pushing, but it's still elastic force. So if I take how many newtons, okay, it takes for me to push this down and open it, I am actually going to run out of newtons. Okay, it is way over 10. Let me try this one. Just so that you know. So this one measures up to 50 newtons. Okay, this one measures up to 10 newtons. Okay, so they all have different, this one measures up to like 2.5 newtons. So I picked different ones based on how big I think how strong the force is. So let me try this one. Everything's so slippery now because of the oil I spread everywhere. So if I try this one, okay, not opening, there it goes. Okay, so it's opening and it uses about 30 newtons of force. Okay, so 30 newtons of force is being used by this, okay, in order to give it back to its original shape, which is like this. I had another one here, right here, okay, same deal. Okay, spring in the back. So how many newtons of force is used to open this one? Okay, and I don't know if I'll be able to get my finger in there to hold it down. No, I don't know if I'll be able to do this one. It's a little trickier. No. Okay, I can't do this one. Okay, oh yeah, there you go. So that was about 20 newtons of force. Okay, that was about 20 newtons of force in order to overcome, okay, the spring force. Okay, actually it's somewhere about 30. Okay, 30 newtons of force, 40 newtons of force, right? So elastic can be both this, the force that the elastic uses in order to get back to its original shape, or another way to think about it is the force that you have to use in order to overcome the elastic force. So the elastic force wants to go back. So how much force do you have to use in order to pull it? Same thing here. How much force do you have to use in order to open it? Okay, so that's elastic force. Springs and elastics are both great examples of those. So if you're looking for something for that slideshow, this is a fridge magnet, okay, with a clip on it. So anything with a clip, okay, I have a clipboard somewhere, okay, and that's going to use elastic force on this, okay. So a clipboard also uses elastic force. This was pretty strong. That's having around 25, okay, 25 newtons of force. So again, you can pick any of those numbers. It doesn't matter which one number you pick. I'm just looking for the word newtons, okay, that you use. All right. So let's see. Quick review. Gravitational force, how much force is pulling down. Shearing force, how much force did I need to cut this paper? Okay, so I use my Newtometer, okay, to pull it down. Magnetic force, how much force was needed to pull it off of here? Okay. Elastic force, buoyancy force. I talked about static electricity force and how we can't, it's very difficult to measure. What other forces are we missing? Are we missing any? Are we missing any forces? I gotta write a list. There should be 9. We talked about 9 different forces. Oh, I don't have the whiteboard up. Okay. So, try to write down. We talked about, yeah, we have them all. That seemed really fast. Friction, okay, pulling this, buoyancy, gravity, electric, elastic, magnetic, tensile, that was another one, okay, that maybe you might have missed. Tensile was the amount of force needed to break a string, okay, I think that's it, okay. So those are all the forces, all right. This has a spring in it, so how much force is needed to make the spring go, okay. I can't even measure that. Maybe 1, okay. So forces are all around us. Maybe, so now, okay, your one task, still very slippery and oily. Your one task, you could, okay, and because you are here listening, okay, I'm going to give you another option on that slideshow, all right? I'm not sure where the directions, maybe you just need to listen carefully. If you want to, okay, instead of doing a slideshow of around the house, okay, of 6 different forces that you see around the house, so magnetic, right? You can see that on the fridge magnets, other things, okay? You see what I mean with that. Or you can do that Canada's Wonderland virtual tour, okay? Pick a ride, all right? And I still want it in a slideshow. Pick a ride and tell me what forces you needed to make that ride go, all right? Don't use electrical force for like powering the roller coasters, because that's a different kind of electrical force. All right. So what 6 forces do you see in Canada's Wonderland? And just you can just tell me the ride you're thinking of. Okay. Tell me the force, the definition of the force, and how you know. Okay. So that how you know shows me that you understand what that force is. All right. So we talked about the swings. Okay. So the swings going around you could use for tensile force on those chains. We talked about the roller coaster. Okay. The gravity. Okay. Going down. Okay. Gravity pulling it down. That's gravitational force on the roller coaster. So what other forces do you see in Canada's Wonderland type environment? So you can use that tour. If you can come up with your own out of your brain, that's fine too. If you're looking for one for elastic, right, bows and arrows, right, that's elastic force and shearing force. So 6 forces, Okay, and because you're listening, you can use the option of either 6 forces in your home or 6 forces used at Canada's Wonderland, and you can use either one of those. Any questions? Any questions? Oh, let me pull this up. Try not to get oil on it. Oil was a terrible idea, Jacob. Just made a mess of everything. All right. Any questions on a different type of forces? Next week, you'll talk about work, which is why this gets really important. Okay, because work is, great question. Nerf gun, typically, sorry, let me go to our Nerf gun place. Huh. You have different kinds. So if I go to our Nerf guns, okay. Again, one of the advantages of teaching at home, you ask a question, I can go find it. Okay. I'm guessing spring. Okay, elastic force. There's got to be a spring in there somewhere. Some of them do work by compression. This is an electrical one. Okay, and I don't imagine that it's going to have a spring in there bumping back and forth and back and forth. I bet you it's going to pump some air in there and then fire it out. So this one might actually work by compression. This is an electrical one, so it's not working right now because the batteries are dead. Okay, but I think you'll hear, right? And that's pumping air into it. Okay, so this one probably works by compression. This one probably works by spring. Great YouTube video series is watch the guys that alter these, okay, and see what they do to them. That would also answer your question because they put like massive springs in them, and it's unbelievable what they do with them, right? And how far they can get them to shoot. Okay. Jacob's looking through a Nerf gun collection. So yep, Jacob's right. Elastic and probably compression. Okay, so this one Jacob's pointing out that you can see. Okay, thanks, Jacob. Okay, so this one you can see the spring in there. Okay, now that's pulling that down, but you can also see the spring. Oops, you can also see the spring right here. Okay, so this one works definitely by spring. Okay, by elastic force. Okay, desires to get back to that force. So that's a really good question. I should use that more often in classes. But I'm pretty sure this one's going to work by compression. Other questions? Other questions? Okay, so I would definitely include Nerf guns if you're going to do forces around your home. Okay, Nerf guns would be elastic, unless you have electrical one, and that's compression. Friction force, I mean, bicycle brake works by compression, friction force. Drawers, why you need force to pull on drawers, right, is because of friction force. I suppose you could use that one. Gravitational force is the reason why you're on the ground. That's a little tricky to show, but you need to find something that works by gravitational force. If gravitational force wasn't there, it wouldn't work, and I can't think of an example of that. Okay, maybe any type of exercise machine would work by a gravitational force. Because it's science, Isaiah. You can't just do science without having a lesson like this. You know that. All right. Any other questions? Any questions besides Isaiah's? All right, fill out that sheet, hand it in. Again, you guys, because you were here, have the slideshow option of either Canada's Wonderland. Thanks, Isaiah. You have the option of either Canada's Wonderland or forces around your home. Okay. Thank you so much. Now I got to clean up some oil.